Assalamu alaikum, everyone. Let's start with today's lecture. We shall be, as usual, reviewing some of the past slides. And we have issued the first homework assignment. How many of you have received emails about that posting? And I hope some of you had a chance to take a look at the homework. So we'll discuss it very briefly and just to give you some guidelines. And then we'll start with, we'll continue with the search strategies. We looked at DFS, BFS, which were uninformed searches. We'll continue with uniform search, which is also an uninformed search. And then we'll talk about informed searches, and we'll talk about two of those examples, best first search algorithm, which is also referred to as a greedy algorithm. And also we'll talk about the heuristic search, okay? So these are the slides as in the past. I will very quickly go over these. This was the search tree that we spoke about, breadth first search, depth first search. And then we spoke about the implementation, how the queues work, the LIFO and FIFO queues. Then we spoke about how do you measure several factors that we look at when we're looking at performance criteria. So we look at completeness, optimality, then the time complexity, space complexity of these algorithms. And we looked at the space and time complexity of both BFS and DFS. And we saw that there were certain problems with both of these uninformed searches. So, right, DFS had its own problems and BFS had their own problems. And one of the problems that was particularly prominent with BFS, the breadth first search, was that it required a lot of space. And if the branching factor was large, then B to the power of something becomes extremely large very quickly. Okay, so you can see that the space requirement becomes very large very quickly if B is large. For example, in this case, B is assumed to be 10. Okay. And we looked at the trade-off between the search cost, the path cost, and what we defined as the total cost, which was simply a sum of both the search cost as well as the path cost. And we said that if you're spending too little time on the search, maybe the optimal path cost may not be achieved. If you're spending too much time on that, maybe, or good enough time, we might be able to get a good path cost. Okay. So now the question is, how do we improve the BFS or DFS algorithms? Okay, so we've already seen that the space complexity of DFS, depth first search, is good. Okay, it's not exponential at least. Okay, it's of the order of B times M, the branching factor, times M, the maximum depth at which the solution is achievable, the goal is achievable. However, the problem is that if the depth is very large, then obviously you go into perhaps an infinite loop as well. Okay. On the other hand, BFS has a problem with space complexity. The space complexity is exponential. It's order of B to the power S. Okay. And if branching factor B is very large, then obviously BFS performs poorly. Okay. So my question to all of you is, can you think of an uninformed search? We haven't talked about an informed search yet, so you don't know what that is. But restricting ourselves to the same domain that we sort of blindly searching, can you think of ways to improve these? And we spoke about this a little bit last time. Maybe some people actually had hints at this. But can people remind us what could be possible ways of actually improving on either one of these two searches? Any thoughts? How do you avoid, DFS is good because it doesn't take exponential space. But what's the problem and how do you actually avoid that? G. You'll have to speak up. It's called record. Okay, so we're taking a depth first search and you're keeping record. So by keeping track of the states that we've already visited, we can avoid infinite loops. That's a good point. However, the problem right now is not really infinite loops. It's simply that the depth of the search could be very large. Okay. And if in all practical problems, a lot of the cases, even if you don't have an infinite loop, for all practical problems, the depth can be very large. Okay, and you might get stuck, even though it may not be infinite, but it could be extremely large. And if you go down one particular deep path, like going down a rabbit hole, and then the other solution, the goal may be right next to you, but you're avoiding that because you don't want to do BFS because you don't know how much space it might take because of the branching factor. So, any thoughts? How else could we improve? G. Okay, so yeah, that's kind of complicated because what you're saying is that we look at the depth of each path. All right, so here's a path which is going this way. Here's the path which is ending over here. Here's a path ending here. Here's a path which is ending here. What you're really saying is that we look at all the possible paths and then we start with maybe the shallowest path. Is that the idea? Okay, what's the problem with doing it this way? Can one think of G? Okay, that's one problem. So you may actually end up going this way, whereas in fact the goal is over here and the goal is not here. That's one problem, G. Yeah. So actually, you basically saying solve the problem and then use the shallowest path. So actually, the problem itself is finding the depth. Okay. To be able to determine the depth, you actually have to traverse this. Okay. And traversing itself is the problem. You understand? So as has been pointed out, that's actually avoiding the problem. Okay, so the problem really is that you really don't know how deep a particular path is unless you actually go down that path. So what do we do? Um, any further? We had some suggestions. Hmm. Hmm. Okay. Okay, that's interesting. Based on your data structure scores, what you're saying is that if the data has already been arranged in such a way that you know that all the short paths are, let's say, on the right side and all the longer paths are on the left side, then perhaps we can sort that out. Okay, and we can use the data structure itself to be able to find a solution. So that's an interesting thought. And we'll hold on to that and we'll see if we can come back to that at a later stage. Okay. Any other thoughts? So what's the problem with depth first? I mean, you're going down extremely deep, right? How can you simply avoid that? G. Yeah, so you could set an upper bound, right? So you could simply say that let's not go too far deep. If you're realizing that this is going down, let's say a certain large value, let's say is going up to 100 deep, then at some point that 100 level will be sort of a flag which will tell us that, hey, we're going too deep, let's stop over here, we'll search other paths, okay? So essentially what we're saying is that we limit our depth search, okay? Because depth is good, depth first search is good because it doesn't have the branching factor problem. Uh, but the question with that begs another question, G. Okay. Okay. So that's sort of similar to this, that we use the data structure to resolve the problem. Okay. So as I said, we'll come back to that particular issue, but let's assume that we're not using the data structure we don't have a balanced tree and so on. Okay. Okay, so that's interesting. What you're saying basically that we use, sort of the power of GPUs, that we have multiple things going on at the same time. So that's interesting as well. That instead of having one CPU, you actually have multiple CPUs or GPUs or what have you, and you're doing a parallel search. Okay, so those are getting into advanced concepts, and let's hold on to those things, and we might come back to those later on. Okay, because those need to make some assumptions. But one of the things which is very obvious is that we could limit the depth. But then the question is, where do we limit it? You know, do we limit it at 10 to the power 2? Do we limit it at 10 to the power 4, 10 to the power 5, 10 to the power 10? Where, okay, and we really don't know. It's a blind search. Okay, so we really don't know where the actual goal lies. Okay, so we have really no idea about the actual tree. So that's one thing that we will look at. And if you look at this example, this is so another possibility could be that we could use an iterative deep search. Okay, so this is something that is used over here. So you start by saying, let's sort of do breadth first, and we'll limit ourselves to a certain depth. Okay, and if we don't find a solution at that level, then we'll go deeper. Okay, so here's an example of that, and this is called an iterative deepening search. So we're starting with a level of 1. So we'll do a level of 1, and we'll do a breadth first search. Okay, so you can see that we'll search for all of these. We'll search for both of these neighbors. Okay, and because we know that the depth is limited to 1. Okay, next what we'll do is we'll go to level of 2. Okay, so this is the tree which is level 2. Okay, and what we're doing is we're looking at this part on the left side, and eventually we're looking at all the nodes, but limiting ourselves to a level of 2. Okay, G. Which is what exactly? So yeah, so the complexity, but the issue here is that you're doing a breadth first, and you're sort of doing a breadth and depth combined. Okay, but you're right, it does seem to have the problems that are associated with breadth first search. Okay, so what it's doing is at level 2, it's now going to depth first. Okay, so it's not looking at all of these neighbors over here, but it's trying to look at, for example, over here, it's looking at these two guys and then continuing on over here. Okay, so it's sort of a combination, but you can see that it has problems as well. It's sort of a mixture of, you know, it seems to have the same problems that are associated with breadth first, and, you know, it could naturally not be a very good algorithm. Okay, but it is one of the recommended algorithms, and you can take a look at it in more detail. It's also explained in the book. Okay, so a problem that I've given to you is I've given you first in the homework assignment that you've just seen, and I've come up with sort of my own algorithm. I don't know if it's been published anywhere. I presume it is, because I just, you know, took 10 minutes and thought of an algorithm. Okay, and here's the algorithm. So start with a breadth first search. Okay, and you decide what is the maximum branching factor that you know, sort of like the depth first search, in which you're limiting yourself to a certain depth. Now I'm applying the same algorithm to a breadth first search. Okay, but a little different, in a slightly different way. And this is the problem that you actually have to code. Okay, so be prepared for this, and you have a week to do this. So I'm going to give you 2 arguments. Okay, I'm going to give you a graph. Okay, it could be some random graph, and I'm going to give you a constant, which is the maximum branching factor that I want you to use. Okay, so in this particular example, I'm saying, let's say that the maximum branching factor B is 2. Okay, so what I'm going to do is I'm going to start using breadth first search initially. Okay, and then if I look at the branching factor at the root level, somebody has to turn off the mobile, right? So if you look at the branching factor at that level, so at the root level, in this case, what's the branching factor? Over here, what is it? It's 3, right? And the algorithm says if branching factor, if the actual branching at that level is greater than the limit that we specified, I want you to switch to DFS. Does that kind of make sense? Okay. So what are we going to do over here? With B is equal to 2, tell me what the search would look like. You'd start off with A. Where would you go next? You naturally go to B. Okay. Now, as you looked at all the neighbors of B, what do you realize? That the branching factor is greater than B. So what are you going to do? Switch to DFS. So where are we going to go next? So we're going to go to E. Okay. Now E doesn't have any more neighbors, so we're going to go back and we're going to go to C and D. Very simple. Okay. Let's take another example. Suppose that B was 3. In that case, what would we do? A, B, C, D, and E. So this would simply be your normal breadth first search because the maximum branching factor is equal to or less than the limiting. Okay. Let's take a look at another example. So let's say B is equal to 2 over here. You would start off with A, and then you'd go to B. What would you do next? You'd go to E. And now what you're doing is you're applying the algorithm at every level. Okay. So at E, where would you go? Sorry, at B, where would you go? After B, E, and then? Now B is equal to 2. So somebody said F, right? Why? Because the branching factor is equal to B. It has to be greater than B to be able to go into DFS. Okay. So I'm going to explore both of these because the branching factor is only 2. Okay. So I'm going to do A, B, E, F. Okay. Now after that, I'm going to go next to the next level. I'm going to look at G and also the neighbors. Now the branching factor is what? 3. So what am I going to do? I'm going to switch to DFS. Okay. So after G, where am I going to go? J. And after I'm done with J, I'm going to go back to H because these were unexplored. H and I because now I'm going back to breadth first search. And then I'm going to go back all the way because F has already been explored. It's one of the visited nodes. I'm going to finally end with C and D. Okay. So this is sort of my own algorithm. Okay. I don't know if it makes sense, but does it make sense to you? It seems to be perhaps better than the iterative algorithm, which seemed to have problems. I haven't worked on this more. Maybe an advanced question, which I haven't asked you, is what's the space and time complexity, but I'm not asking you to do that. All I'm asking you to do is to actually code it. And not too difficult, right? You guys are in the 4th semester. You're already coding gurus, right? Okay. But I'm going to give you some hints as well. Okay. So if you look at the actual homework assignment, which I have somewhere over here. So this is the second part. Actually, the first part is a bit easy. So I've given you, I don't want you to use any algorithm to solve this. Why is that? My reasoning is that because sometimes you might actually find the entire code available online and you can just plug and play. Okay, I don't want you to do that. I want to give you a starting place. So you sort of restrict it to a certain algorithm. Okay. And that actually happens a lot in real life. If you join, let's say, a big company and there's a ton of code already there and you have to solve a problem, you're not going to say, I'm going to change the entire code, right? I'm going to write the whole thing from scratch. No, you have to actually understand the current problem and then solve the problem. Okay, so you have to understand the existing code and then to remain within that set of rules or set of assumptions. Let's say it's not using object-oriented programming, it's simply using functions. So stay within that, and now rather than completely changing the code, make slight modifications to it. Okay, so this is what I want you to do. If you look up DFS, BFS, one of the first pages that you'll come to is these 2 sites. Okay, and they have good implementations of both of these algorithms. If I sort of jump to those sites, so here's the code. You can take a look at it. I'm not going to go into a lot of detail, but it gives you a graph in a certain format, and it uses for depth first search, it uses a certain type of algorithm. Look at it, understand it. Hopefully it shouldn't be very difficult. But I would like to make a point here, and sort of I'm changing what I initially said. Some of you asked me whether we can use any language in this course, okay? And at that point, I had said yes. Now, I'm sort of switching and changing that statement. There's a reason for that. So a lot of universities such as Berkeley, Stanford, what they do is they use what is called an auto-grader, okay? Some of you might be familiar. Most of IBA people are not familiar with that. None of my colleagues are familiar. But I've been able to get the source code from Berkeley, from a source from Berkeley. Berkeley provides it generally free, as long as you, accept that it's from Berkeley. And the autograder, what it does is basically makes my life and the TA's life easier, okay? It also makes the job of actually grading your homework assignments a lot more accurate. So what the autograder is going to do is it has a very complex code, and right now it's based on the assumption that it's Python code, okay? So that's one of the limitations. And generally, it's a good idea in AI to actually learn Python. So if you haven't learned it, I think this is a good time to actually start learning the Python programming language in this course, okay? So what the autograder does is it takes your code and it applies, it takes your code either as, an object-oriented, or, it either accepts your methods or it accepts your functions, and then it will pass on, an object or arguments. For example, it will pass on a certain graph, right, with a certain value of b. And you need to provide a certain output, okay? And the output that I'm asking you here is simply the letters that, simply the order of the output. So in this particular case, for example, the one that I just showed you, I'm just looking for A, B, E, F, G, and so on, the order of the search. There is no goal here. You're simply traversing the entire tree, okay? And I'm going to test this using the autograder by providing a certain graph with a certain set of adjacencies, which are defined over here. This is the adjacency matrix. And it's going to test whether the result is correct or not, okay? And the TA will presumably have a bunch of examples that he is going to test your code on, okay? You don't know what examples, what the test cases that we have, but as long as you can solve, some of the basic, graphs that we've provided you, it will hopefully work for more generalized cases as well, okay? So, so the autograder requires that you use Python. So that's why I'm going to be requesting all of you to actually code in Python, at least for this homework assignment, okay? The further details of the assignment are given over here. So if you look at the details, it does ask you to do very specific things. For example, because it's expecting a certain output in a certain format, you have to be very particular as to how you are actually providing the output. So, don't assume that somebody is going to be looking at it. It's going to be automatic, okay? So if you have too many spaces in the output, or if it has a curly bracket, it's going to throw off the algorithm, okay, the autograder. So we've given you all the do's and don'ts over here, and hopefully once you've got an idea, the subsequent homework assignments will be easier for you to do, okay? Read through this carefully, and the submission assignments are given. You've got to upload it on LMS and so on. If at any point you have problems, we do have a very good TA, 2 TAs, Nida and as I mentioned, Hamad Javed, who's in 8th semester, and both of them will be available to help you with it, okay? Just a small warning again, you can discuss with your colleagues, but please don't blatantly copy, okay? And if you do that, we have other means of checking plagiarism, and if that happens, then all concerned parties will end up getting a 0 on that assignment, okay? So please don't do that. So that was the second part of the homework assignment. And let me also very quickly talk about the first part as well. The first part is it refers to one of the puzzles that is often referred to in AI, which generates trees, okay? And this is the frog jumping problem, okay? And if I take you to the website which actually implements this, it's kind of fun as well to look at it. It basically says that there are, well, in this case, there are 3, but let's say we reduce this to 2, okay? Or let's keep it really simple and say there are 2 frogs, one on the left, one on the right, blue, red, okay? And the rules are that the red has to go on to the other side and the blue has to go on to the other side. And the only possibilities that they have are the rules are given over here. Naturally, blue can go forward, okay? Now red can jump over it, okay? And blue can go forward. So you can see this is a solution. It's found the solution. But this was a really trivial case. If you increase it to 2, it becomes a bit more tricky. For example, if you're going right, okay? And both of these blue frogs go forward. Now the red frog can't make 2 jumps. It can only jump over 1 frog, okay? And it can't go backwards either. So now you've actually, you sort of stuck, you've hit a dead end and you've lost the game, okay? The solution, if you reset this, as you can imagine, would be that you go this way and then maybe this way, this way. No. Okay, so you can figure this out, all right? It's not trivial, but as the depth goes on, it becomes more and more complex. And this is a tree. Now, how do you think, what's the branching factor in this tree? For at any state, so the state is given by the state of the frogs, right? What's the branching factor? How many actions can you take at any given state? Sorry? I heard 2. Depends on the number of frogs. Okay, so let's increase the number of frogs to 3 or 4. Okay, how many steps, how many actions can you take? 2. It's actually 2. Okay, you can either go, you can either move the blue frogs, or you can, if I reset it, you can move the red frog. Okay, so play around with this a little bit more and you'll realize that there are only 2 paths. Okay, and you can either move leftwards or rightwards. Okay, so if I reset this, you can see that this movement I'm calling a right movement. Okay, and if I do this, this is a left movement. Okay, so two possible actions: a left movement or right movement. Okay,
sir.
Is there a question?
Yes, sir. Even though अगर हम stuck हो जाएं, लेकिन left side से या right side से jump तो कर सकते हैं ना?
No, once you're stuck, you're stuck. For example, if you
नहीं
do
sir,
this,
आप कह रहे हैं sir, 2 possibilities हैं.
So the possibilities are, the rules are given over here. Basically, it says that you can't go backwards. So the red frog can't go backwards. This guy can't go backwards. Now the blue frog can't go forwards because it can't jump over 2 frogs. Okay, so this is a dead end. Okay, look at the rules a little bit more. If you're confused, just play around with this. It's an interesting game. But if I look at the search tree, so what we're going to define this in this particular case. So for example, in the case of just this case where you only have n is equal to 1, okay? Sorry, I think n is equal to 2 in this case. You have 2 frogs. So I'm showing this as 102. Why? Because the blue corresponds to a 1. So this is a blue over here, and this is the red over here. And reds are called 2, and blues are called 1. And so if you look at the first 2 actions that can be taken, if the blue goes to the right, okay, you go to the right, what's going to happen? This guy comes over here, and this becomes, so an empty space is defined as a 0, okay? So the left space becomes 0, and the blue frog comes over here in the middle, so that becomes 0, 1, 2. So that's a new state. If the red frog moves to the left, then what's going to happen? This guy is going to go here, so you're going to have 1, 2, and 0. Okay, so I hope that's quite obvious. And similarly, you can keep on going in both directions. So this is the branching factor is at maximum 2. Some of these you can't take. So this is sort of not a complete dead end, but the left side is a dead end, but the right, you can still go make right movements. In some cases, you'll see that you end up with a complete dead end, not shown over here, okay? If both of these become a not possible, then it becomes a dead end, okay? So this is referred to as dead end. The goal is, of course, to get into one of these two states. This is both the same state. 201 means that you actually have, the right frog has gone on the other side and the left frog has gone to the other side. Okay. Now you can get to this in different ways. So in a tree search, remember, it's a directed search. Each state, so this is actually the same state, but it can occur twice in this tree. Okay. Why is that? Because the tree search is going through certain actions, right? So it's going through certain actions. Each state has got a parent. Okay. So the parent of this is different from the parent of this. And that's why it occurs differently in the tree search. Okay. So, so your objective is actually to draw out by hand the tree search, the tree. Okay. So this is exactly what you have to do. There's no coding in the first part. It's a simple simple problem. Okay. It will become a little big, as you can imagine. This is referred to as a binary tree. Why? Because it's naturally, each time it's actually bifurcating. Okay. So that's the homework assignment. Hopefully it's not too difficult. So, so what we started off by looking at, and we said that what are possible ways to improve the DFS and the BFS. So by hopefully implementing the homework assignment, you're actually getting one step closer to actually coming up with a new algorithm. You may not find this anywhere, which actually improves the existing uninformed search. Okay. There's one more category of uninformed search that we need to next cover. What if the cost is not the same? Okay. What if the cost is not the same? So far, what we've said is that the breadth first finds the shallowest goal. Okay. But it will find the optimal solution if all the steps are the same. Okay. What if the steps are not the same? Okay. So then it becomes a little tricky. Okay. And the algorithm that solves this is referred to as a uniform cost search. What it does is it slightly modifies the breadth first. Okay. And it says that let's only expand the lowest cost node. Okay. So let's take a look at how this does it. So here's a problem. Now, what you find different in this problem is that, first of all, it's a goal-based. So you have a starting point. Okay. You have a final goal. Okay. And what else do you notice is different about this particular graph? It's got weights, right? So it's got a cost which is not one. So earlier, so far, we had assumed that these were all unit costs, but now we actually have a cost which is different. Okay. Is this a tree or is this a graph? This is a graph, right? Because a tree would not have any, each one of them would have a single parent if it's a directed tree. Okay. So now the question is, how do we solve this? Let's try to solve it using the following algorithm. It's going to modify the breadth first search by always expanding the lowest cost node. Okay. So let's try to do it. And we'll use our queue. Okay. That we use this, remember in the BFS, it was a FIFO queue. So what are we going to do? We're going to look at node A and we're going to add node A over here into the queue. Now what we'll also do is we will expand by expanding the lowest cost node, which is measured by the path cost. Now remember, what was the path cost? Was it the single step cost or the entire cost? From the source to wherever you are. That's the path cost. Okay. So it's a sum of basically each step cost that you've taken. Okay. So what we're going to do is we're going to, let me just put this on mute. So we're going to have we're not only going to look at the usual BFS, but we're also going to look at the path cost. Okay. And this will prioritize those nodes in the queue which have the least path cost. Okay. That's the basic idea. So let's go forward. After A, what are we going to, let's assume that we go from the left side. So we're going to look at B, okay? The cost so far at A was naturally 0. The path cost till B is what? Is 10, okay? We'll also, in the BFS, we add all the neighbors, okay? So we're going to add C and we're going to add D. So C's has a path cost of 20. D has a path cost of 25, okay? Now, what it's going to do is it's going to prioritize the nodes based on the path cost, okay? So in this case, it's already prioritized. So now, next we're going to look at B, okay? Now, B is going to look, the neighbors of B, there's only one neighbor, which is F over here. What's the cost to get to F? 30 plus 10, which is 40. Okay, so 10 plus 30, which becomes 40. Okay. Now, once you've done that, we've explored B. Now, what we're going to do is go back to the breadth first. We're going to look at C. We're going to take this path. So we've already taken this path. Now we're going to take this path. And we're going to look at the path cost to get to the neighbor of C. And what would that be? So G over here is coming out to be 40. G over here is coming out to be 45. Okay. So is that lower than the earlier cost? No. So we'll forget about this. So this is not very good. It's not very useful. What about the next one? So the total cost till from via D is coming out to be 30. Is that less than 40? Yes. So we'll actually say that we're going to prefer this path. So this will become our preferred path. Okay. Why? Because we found a shorter way to get to the destination, which is at a cost of 30. Okay. So I haven't gone to all the implementation details, but this is basically what it's doing at a high level. G. Yeah. So again, I'm giving it to you at a high level. If I go into the actual implementation details, it will take me a lot longer. So I'm just trying to explain to you. I'm not going into the actual details of the implementation, but I'm just trying to explain to you how it would work at a logical level. But if you actually try to implement it, you would need to have a lot more data structures. You'll probably need to have a visited node and other things, okay? But I'm not going to go through that yet. It does become a little complex. You can find a lot of, if you search for implementation of uniform cost search, you'll find solutions on the internet, okay? But again, I'm not going to go into so much detail. Okay, so now this was a uniform cost. Now the question is, what are its properties? So the first question is, does it seem to be complete? What is the definition of completeness? Whether it will find a solution. If a solution exists, whether it will find it. So do you think it will find a solution? Yeah, so because it's doing a BFS. I mean, you're doing a BFS, you're going to find every possible solution. So it is complete, yes. Is it optimal? Okay, so it seems to be optimal, okay. Yes. What about the time complexity? So it's traversing all the nodes, so it's going to be somewhat exponential, right? And the breadth first search, and because it's a breadth first search, how much space is it going to take? So not very good, okay? So it depends, I'm not going to specify exactly what X is over here, but it is an exponential time, okay? Both time and space are exponential, and you'll have to be able to figure out what X is will take a lot more time than we actually have, and that's not really our objective right now, okay? And yes, it is optimal, and it's not only optimal for the step cost, which was in the case of one for BFS, which is already optimal, but now it is optimal if the costs are now varying, okay? So now we've come one step forward from a BFS, okay? Especially for the cases where you have varying costs. So that sort of completes the search algorithms that I'm going to go over. There are other search algorithms in the book as well, but I think these are sufficient for the time being as far as uninformed searches are concerned. Okay, and you can take a look at you can practice this as well, but I have had some more complex examples, but I'm not going to go over that. So now let's think about some real world problems, okay? And in these real world problems, sometimes you actually have more information, okay? So here's a problem. This is where you live, right here in defense, okay? You have to get to IBA. And let's assume for the time being that Google does not give you the optimal search route, okay? This is the old-fashioned ways. I remember that when I was young, when I had to go somewhere, especially in the US or somewhere, we had these maps, okay? We open them up and somebody would actually be helping with the route, and they would look at the map and say, where do you want to go next? Okay, you didn't have the Google Maps at that time. So let's say that you didn't have that. Which route would you take? Would you take route A or route B to get to IB main campus? A, why is that? It looks shorter, right? Why is that? Why does it look shorter? First, for several reasons. If you just look at the map, if you think about the distance to if you take the shortest distance, this seems to be, if I took this, it seems to be shorter, right? If you took this path and you just made it longer, it seems to be shorter. Ji. Sorry? आपकी आवाज मेरे तक पहुंचती नहीं है. अगर बी लो तो फिर? Yeah. Yes. So you're jumping ahead, and what you're basically saying is that most likely, this is going through the Lyari Expressway, and somewhere in your mind, you know that Lyari Expressway is fast. Okay. But let's try to take baby steps right now. Okay. So the first baby step that we're going to take is, let's say that we don't know anything about the speed of these. Okay. All we have is some very basic information which simply says what's the aerial distance. Okay. This is a new city for us. Okay. This is not Karachi. This is, let's say, San Francisco. Okay. You've never been there, and you see two routes. You don't know that this is faster, and you don't know that this is slower. Okay. Which route are you going to take? You're probably going to take the one which is, seems to be shorter. Okay. So, and so the rule of thumb, or the intuition that you're using, is the aerial distance. Okay. You're simply saying, well, this seems to be shorter, so why take a longer route when I don't know if it's better or faster or what have you. Okay. So this is what is referred to as a heuristic. Okay. So this is what is referred to as a heuristic. And heuristic basically starts getting into basically artificial intelligence. And that's why we're studying this in this course and not maybe in a data structures or algorithms course. Okay. You probably haven't studied heuristics in the algorithms course. So heuristics basically says that, can we have a rule of thumb, an intuition that will help us to get to the goal? And now that intuition is basically giving us some additional information, and that is why this would be called an informed search. Okay. This is not uninformed. You're not completely in the blind. Okay. You actually do have some additional information that is going to help you with the search. Okay. So all informed searches will give you some additional information. So now, now that we've understood this, let's try to think about what could be possible heuristics. So here's the 8 puzzle that we looked at earlier. Okay. And let's try to think about what could be possible heuristics if you wanted to use this. Okay. In the GPS, it was quite obvious, right? In the shortest aerial distance, right? As the crow flies. But here, it's maybe not quite obvious what should be the heuristics. So can people come up with heuristics over here? So here's the start state, okay? And here's the goal state. So you have different, as you saw, the number of possibilities could be extremely humongous, okay? So you don't want to take all the possible paths because that would take forever. So you want to apply a heuristic, and we want to say, we have these 3 possible actions that we could take. Can we come up with a heuristic which will tell us which one is actually better than the other? So what could be a possible heuristic? G. Sorry? Moving 3 upwards. Okay, so you're saying that, well, that's a very specific action. Let's make a general rule of thumb. So convert that into a rule of thumb. Okay, so basically what you're saying, because the goal has all the small numbers at the top and all the big numbers at the bottom, your goal is to try to get the big numbers to the top. Okay, so can we convert that into a heuristic, into something more specific? Because that's still too general and that's still too human-like and too intuitive. And the algorithm wouldn't be able to follow that. Okay, you have to convert it into something very detailed. You have to write it down as an equation, or at least write it down in a sentence. What would be a heuristic? Convert the same thing into a heuristic. Gee, let's come back, stick with the gentleman here. Okay, yeah, ठीक है. Some other suggestions. Okay, so basically हमें 1 को जो है, we need to take it all the way up till here, right? So and 2 has to go from, well, 2 doesn't have to go anywhere, so that's good. Okay, 4 has to eventually get here, so it has to come down over here. Okay, so can we start converting this into a heuristic? Which one would be better versus which one would be worse? Suppose that you have 2 possible actions. Which one would you say is better or worse? G. So we could assign points and we could say that, so let me help you out over here. We could say that how far, let's say we've got a new solution. So 3 went upwards over here. So we've got the 3 over here. And what we're saying is that, is 3 getting better to the original, to the destination? Okay, it seems to be getting better. So what we could say is that let's make a heuristic, and I'm going to call it H1. That's how it's normally called, for a particular state. So this is a state N. Okay, this is another state M. Actually, this is a goal state. Okay, so let's say that we will count how many, what's the distance from the destination for each one of the blocks. Okay, so for each one of these blocks, if by moving 3 upwards, we're getting closer to the destination, then its heuristic is going to be smaller. Okay, so let's count. So in this case, for the case of 1, how far is it from the destination? How many steps would it have to take? Well, it can't go diagonally, right? So we're going to call this the Manhattan distance. I don't know if anybody has been to Manhattan in New York City. It's like a grid. Everything is, going, you can't, it's all vertical streets or horizontal streets, right? Avenues and streets, that's how it's called. Spent 8 years over there, believe me. It's not good traffic. So Manhattan is, the Manhattan distance is referred to as how many steps would you have to go this way versus how many steps would you have to go this way. Okay, so 1 would have to go how many total steps? It would have to take 1 step, 2 step, 3, and 4, right? So 1 would have to take 4 steps. Okay, 2 would have to take how many steps to get to the goal? 0. 3 would have to take how many steps? It's over here, so it would have to go 1, 2, and 3, and so on. Okay, so you could come up with a total number which gives you the total number of steps that the current state would have to take to get to the destination. Okay, and if you moved 3 up here, naturally you would be 1 step closer to get to the destination, because in this state 3 will only have to take 2 steps as opposed to 3 steps. So the heuristic number would become smaller. Ji. Yes. So it's actually, so the point is that the point that you're making is that will the heuristic always lead you to better states? It won't, right? Because heuristic is, after all, going back to this case, as you rightly pointed out, that here you may have a huge traffic jam, right? This whole area might be completely traffic jammed. So a heuristic is a partial information, and it's only trying to say, well, let's try it, okay? And because we don't know anything better. But as soon as we get over here, we find that, oh my God, there's a huge traffic jam. And then we realize that, maybe this path would have been actually better. Okay. So the same thing over here is that you might realize that by taking 3 over here, it might actually get us into a worse state. Okay. And if you're really intelligent and you knew the whole thing, you might actually figure out a much faster way to get to the destination. Okay. So heuristics, are they always good? They're not always good. Okay. We can imagine that. Just like in the other case, heuristics are not always good, but it's better than anything else that we have. Okay. So you have to start somewhere. So there are a couple of heuristics that are used in this case, and I'll show this over here. So the one that we're looking at was the Manhattan distance of the goal. Okay. So in this case, if you look at it, as I was saying, it would be 4, 0, and if you look at the rest of the tiles, it comes out to be 14. Okay. So that's the current heuristic for this state. If you call this state 1, then this is equal to 14. Now, the question is that if you have 3 different directions to go into, and this one has a heuristic of, let's say, 13, this one has a heuristic of 12, this one has a heuristic of 15, which path would you choose? You would naturally choose the one which reduces the heuristic to the best. Okay, I don't think in this case it's possible to get a reduction by 2, but you'll have to work this out. Okay. And you would naturally pick something which is getting you closer to the destination based on your rule of thumb. Okay. Another example is H1, which is simply saying number of misplaced tiles. This is a little easier. So if you look at the number of misplaced tiles, it says that the answer is 7. Can somebody tell me, is it really 7? Can we count that? Is 7 in the right position or wrong? It's wrong, so that's 1. Is 2 in the right or wrong? So it's right, so that's 0. That's 1 plus 0. 4, is it right or wrong? It's wrong, so that's 2. Wrong, 3. Wrong, 4. Right. Wrong, 5. Wrong, 6. And wrong, so 7. So 7 tiles are misplaced. Now we're not looking at the distance, but this is also an example of another heuristic. Okay, it's a rule of thumb. Which one actually works better, we really don't know. Okay, but you could test this out and play with this, and you could maybe come up with other heuristics as well. Okay, but this is an example, a couple of examples of heuristics. Think of other examples. Somebody mentioned the other time, it seems like chess is my favorite game. Yes, it used to be my favorite game, so I will always refer to chess. In chess, what could be a heuristic? So what are you trying to do in chess? Okay, let's say you're white and the other person is black. What is your final goal? To win, right? I mean, intermediate states are worthless. Your overall goal is to either win, you're either going to win or lose, okay? But what could be a heuristic? How could you gauge, if you're not a grandmaster, you're doing a very simple level of chess game, how would you train your, a little sibling how to play chess and which position would be better? Okay, so you've got your pawns over here in front and you've got your queen over here and rooks and so on. What can you come up with a heuristic for this? How would you guess? How would you say which is better, which position, which action is better, which is worse? G. Okay, so you're right, but that's kind of complex because basically you're saying yes, but that is a complex heuristic, and to be able to gauge whether you can actually defeat somebody's queen in the next step or the king is kind of difficult. What could be even simpler, really simple? Start with baby steps. Number of actions that the opponent can take. The lower the number of actions. Okay, good. So good suggestion. So if you can limit your opponent to very few positions, or maybe the king, if the king can't move at all, then maybe that's a good state. But again, you're thinking very deep. Think of something really simple. G. Exactly. So number of pieces. So you could say that if by taking, if you've got something over here which can if you take your pawn over here, or if you have a horse, let's say, and you're going over here, or let's say the horse is here, you can go here, or you can go here. If you're going here, somebody can kill you, versus here, you're not getting killed. Which would you prefer? Because the one where you're getting killed, you will have less number of pieces left. Okay. So a simple rule, a heuristic could be, how many pieces do you have left? But then you might say, well, are all pieces have the same value? Probably not, right? The queen is much more valuable than a pawn, right? So in that case, you could say, well, the heuristic could be, I could weight the queen by, give it 10 points, and the pawn could have 1 point. Okay, and then you could gauge whether if you're losing a queen, then you're losing 10 points. If you're losing 9 pawns, you don't really care. G. Yeah, so then you're getting into complex situation. Then you need something like, a more sophisticated AI. But all we're saying right now is that for each situation, you can come up with your own heuristics. And you can see that how the game of chess can have a very simple heuristic as well. Okay. And then if you come up with more powerful heuristics, the AI agent will perform better. Okay. It depends on how good the heuristics are. Okay. So let's take a look at this example, and let's see how good this heuristic works. So this is an example where we again going to the distance. So this is a GPS example, simpler case. So let's assume that you have a cost of 7 over here, a cost of 10 over here. Okay. Now what we're saying is that the heuristics are based on maybe distance. As you can see, this seems to be a little shorter. Okay. So the distance over here to get to the destination is, let's assume 15. Okay. So I've given two things over here. I've given the actual costs. Okay. 7, 10, 15. Now the actual costs are not known to us. Okay. Remember that. We only know the first step cost. We only know that from getting, if you make this particular step, we know that the cost is going to be 7. And if you take this step, the cost is going to be 10. Okay. What we additionally know is that the cost, the approximate heuristic cost of going from C till the destination is 15 over here, because it seems that the distance is shorter. And the heuristic over here seems to be a bit longer. As you can see, the path is a bit longer. So our guess is that the heuristic to get to the destination from D is going to be a bit larger than C. Okay, so I've made this 20. Now the question is, what would be a good algorithm? The first algorithm that we look at is what is called a greedy algorithm, or a best first search. Okay. Now why is it called a greedy algorithm? It simply says, I'm going to use the heuristic. Okay. The heuristic says this looks good. Okay. I'm not going to worry too much. I'm just going to jump for it. Okay. So based on the heuristics, which path would you go? Now remember, you don't have this information. You don't know what traffic is going to be when you go onto the Liari Expressway, or you're going to go on to the Shahid Millet Express, okay, or extension. What you do know is going left or right will cost me so much. And you do know that at the end of that particular path, the chances are that this will take me 15 steps, this will take me 20 steps. So what would be a very simple heuristic, the greedy search algorithm? What would take the left one, take C. So it's saying that I'm going to simply choose the node with the least h of n. I'm not even going to look at the costs. Okay, I'm being greedy. So I'm going to simply check C, but do you think C is the best choice, looking at the overall thing? Well, the total cost getting here will be 17, and the total cost over here will be 25. So it seems good. But the question is, will this always be the best? So here's a situation where you have heavy traffic, right? So all of a sudden, the cost over here has gone from 7 to 20, and the cost over here has gone from 10 to 25. Now, this is still visible to you. The first step is visible. You're seeing some traffic over here, and you're seeing that this cost is lower, okay? And this cost is higher, but again, I'm being greedy, okay? I'm going to look at only the heuristic. Now, what is the heuristic saying? Heuristic doesn't really know that the traffic has gone up over here, okay? Heuristic is simply saying that I know that the aerial distance from here is still 15 and the aerial distance from here is still 20, as in the past, right? So the greedy algorithm is going to do what? Is it going to go through C or D? It's still going to go through C, unfortunately, right? Because it's being greedy, it's not really going to look at the big picture, okay? So, and now is it the best choice? So if you look at the total cost over here, G over here will be what? 20 plus 25, which is 45. The G over here would have been 25, right? 10 plus 15, 25. So it would have been better actually if we had gone through D, but we were being greedy and we simply used the heuristic. We didn't even look at the fact that this was of a lower cost, okay? So this is what the greedy algorithm is doing. Now, let's take a look at the next algorithm. And the question is that how can we actually improve the algorithm? Okay. How would one improve this algorithm? Let's say that you do know, the cost of AC, okay? And you have the cost, you have this information, you have this information, you have this information. Without being greedy, can you come up with a better algorithm? You don't know this, okay? You don't know this, you don't know this. But based on the information so far, can you come up with a better algorithm? G. We can add both of these, and when you're adding both of these, what are you basically doing? Sorry? Averaging? Are you really doing averaging? No, because H of C is saying what is the cost to get to the destination from here? And this cost is saying what's the cost to go from here to here? So by adding those two, what are you really doing? You're taking the path cost, okay? So you're saying that based on the heuristic, what is the total path cost, okay? But it's not based on the actual cost, it's based on the partial actual cost and partial heuristic cost, okay? So it's simply a combination of the two. And what we've done is we've said, let's use the cost till here. Let's say the cost till here is G of C is 20, okay? And the cost over here is, and H of C is 15. So what we're going to do is we're going to take H of C and we're going to add, sorry, not H of C, but G of C, okay? G of C is the actual cost, which was 20. And then we're going to add to it the cost to go from C till the destination, okay? What is this coming out to be? 20 plus what? 15. That's coming out to be 35, right? Now, what is, and let's call this F of C, okay? What is F of D? It's going to do 10 plus, what is that? 15, right? So that's coming out to be 25, okay? Now, in this case, which path are you going to choose? Sorry, H of D is 20, you're right. So this is 20, okay? So this comes out to be 30. So which path are you going to choose? You're going to choose F of D, okay? Why? Because you realize that it's sort of very intuitive. You're simply using all the information that you have. The greedy one was simply disregarding some of the information that you already had. So it seems almost, a no-brainer that you would use this, okay? G. Yeah, so you're totally just ignoring the actual path cost. You're simply looking at the heuristic, okay? G. So how are we calculating H of C and H of D? Good question. So this was based on some heuristic, all right? And I used my own heuristic and I said, Well, let's see. This looks a little closer. Okay. If this step was 20, then maybe this is 25. Okay. Just I pulled it out of a hat almost. Okay. It's a heuristic. So I looked at the map and I said, well, A to C was 20. So C to F seems to be a little longer than that. It seems to be 25. Okay. So I said that, I'm sorry. So I said that H of C is 15. Okay, again, I got confused over here. So I used H of C is 15. And then I looked at this path and I said that this path is a little longer. So I'm going to use H of D as 20. But again, this is a heuristic and I'm not giving you any explanation for that. Just an assumption, absolutely an assumption, all right? As I said, it could be based on the aerial distance. It could be based on, as in the puzzle, you're looking at, how far you are. You've come up with some idea. Yes, so as we said, heuristic is not always optimal. It might lead you into a traffic jam and you may get into something. And as we're seeing over here, in this heuristic example, it is not actually, if you're simply using the heuristic, then it's not good. But if you're using the heuristic with some combination of the current cost, it seems to be a little better. Okay. And as we can see over here, the previous case, what were we doing? We were choosing the path C, even though the actual total cost was coming out to be bigger. Okay. By using a sum of those two, that we're using the G as well as H, okay, we've come up with a better algorithm. Okay. And this is what is referred to as an A-star algorithm, which is sort of the best algorithm in most cases. Okay. Now the question is G. What is the? Okay, so G function, as we said earlier, is the path cost. Okay, so I think I've got that somewhere over here. Somewhere earlier I had that. Yeah, so this is the path cost. Okay, and it's sum of all the individuals' costs to get to a particular destination. This is the actual cost. Okay. Sorry. Yeah. So again, let me repeat this. Over here, what we're really saying is that we have. So let me repeat the whole thing. Okay. So what we're doing is we're coming up with an algorithm which is going to say, let me repeat it over here. So here's the algorithm. It's going to say, I'm going to use a function which is a combination, which is as proposed by a gentleman over here, which is now not only going to use the heuristic, but it's also going to use the cost to get to that particular point. Okay, so this is a new function, and this is what is referred to as an A-star search. Okay, this is one of the best algorithms that exist. Not the best, but it is a good algorithm. Okay, and what it's going to do is it's going to say, well, in this case, I'm going to say that which path is better. I'm going to not only look at the heuristic, which was being done in the greedy search, but I'm going to, because the heuristic is saying how long will it take for me to get from here till the destination. Now the actual cost was 25, so the heuristic is mistaken. Heuristics can be mistaken, right? Here the heuristic is 20, whereas the actual cost is 15, but we don't know this. Okay, we don't know this. All we know is our estimate. So what we're going to do, we're going to say, let's take the heuristic, and we know the actual cost to get to C and D. Let's add both of them, which is the information that we have, and that way we will make a much better informed search. Okay? And so if you look at this, FC is taking 20 over here. It's adding the heuristic, 15, you're getting 35, and F of D is taking 10, and it's adding the heuristic over here, 20, and you're getting 30. And so we're going to choose the new function, which is based on the A-star search, and it's going to select 30. Now the question is this going to be an optimal search? Okay, will A-star be an optimal search? Now because we don't know this value, okay, suppose that this actual value is very large. So we've taken ADF, right? But we really don't know what this value is, right? Suppose instead of 15, it was 40. In that case, does it seem to be the optimal route? No, because you're assuming that this is 20, but when you actually took this path, you found out the actual path cost is very high. So it seems like it's not optimal. Okay, but here's the step, here's the part of the A star which I haven't told you yet. What it does is it does one more step. Okay, what it does is it's going to, let's take a look at this example over here. Okay, what it's going to do is it's going to take a look at this path. Let me go back to the same example. Okay, so it's once it gets to the destination, it's still not going to stop there. Okay, so it's gotten over here and it found out that by coming over here, the actual cost was coming out to be what? 10 plus 40, which was 50. Right? Now it's not going to stop over here. It's going to say what other paths had I earlier explored. Okay, what was the earlier path that I had explored? And that was up till C. I hadn't explored this yet, but I had come up till here, right? I had come up till C. And what was the heuristic at C? It was 35. Okay. So I hope people are following me. This is an important point. It's going to get to the destination. It's going to say, what is my total cost over here? That's actually 50. It's going to compare that with my function, the cost over here, with any other open paths that I had previously explored. If this particular path had a cost which is lower than this, I'm not going to take this as the final cost. Okay, I'm going to go back and I'm going to use this path. Okay, so it's going to go back over here and then it's going to continue exploring from here. So when it explores back from C, what do you think it's going to get as a total cost? The total cost is now going to be the actual cost, right? It's going to be 20 plus 25, which is going to be 45. Now, is 45 better than 50? Yes. So it's actually going to disregard this earlier path, and it's now going to say this is the final path that I'm going to choose. Okay? So the thing is, you're absolutely right. Very well pointed out that it seems like this is, taking forever. Okay, because first you're going through one path, and then you're using some heuristics, and then you're saying, well, this doesn't seem to be best path. I'm going to use another path, and so on. So yes, the time complexity is exponential. Okay, so time and space complexity is actually, in the worst case, is actually as bad as, it's even worse than the depth first search. Okay, but then the question is, why is it called A star? It seems like it's a fantastic solution, right? And I also said it seems to be better than other searches. Why do you think it's better? हाँ, so हम heuristics को update भी कर सकते हैं. Right. So that's a good point. So you could update the heuristics, but any other thoughts? Why do you think this is actually better? If the paths are fixed and the what? Costs are not changing, then we can use this strategy. But you see, still, it does have a problem that, and we haven't explained it, that because you're taking different paths and you're exploring one path and then you're going back and you're exploring other paths, the amount of time it is possible, for example, just think about it. You're going from defense all the way to main campus, right? You've used a heuristic and it says, well, to get to, Shahid Milad Expressway seems to be best because, it's my estimated cost to get from there is short. The distance from here to the expressway is short. I'm going to use this. But as soon as you get there, you actually might realize that there's a huge traffic jam and you can't even go back. So what happens? You've actually gone the wrong way and now you're going to explore other ways. So you can imagine that in some cases, in the worst possible case, the A star search can be actually really bad. Okay, so the time and space complexity can be extremely bad. But the bottom line here is that if you have a good heuristic, okay, and that's a big if your heuristic is good, then this can be a very good solution. It all depends on the heuristic. So going back to the chess example, if you can come up with a good heuristic, which is, some of the suggestions that people gave were really good. If those heuristics are used, then maybe that can actually limit your search and you can get a very good algorithm. Check to karega, it might actually end up in dead ends. And so it depends again on the heuristic. If the heuristic is bad, you could end up with a lot of dead ends and you may have to actually, it might take you a lot longer. Okay. But if you have, if you look at any game that you play, we're all playing, unless we are really super genius and we can actually explore all the possible paths, we're actually playing based on heuristics. If you look at any game, I mean, I don't know what games you guys play these days. I know my sons play Dota all the time, but all of those games actually are based on heuristics, right? You're thinking that this will be a better strategy. You don't really know. So if your heuristic is good, you might actually have a much shorter path and you might actually win. So if you look at any one of the big games, like Go is a big game, and the grandmasters of Go actually use a heuristic internally. They don't really have a search tree that can actually think, look at all the possible ways. So let's stop over here. We'll take a closer look at the A-star search a little bit more before we go on next time.